Problem 15. Derive linear density expressions for FCC 100 and 111 directions in terms of the atomic radius r. And in part B, compute and compare linear density values for these same two directions for silver. So let's draw first these directions. 100 will be this direction. This direction will be 100. Okay, so for this direction you can find the linear density expression. So linear density means number of atoms in some particular direction divided by length. Okay, so if the length of this unit cell is A, so A is in this direction, A is in this direction, so all three dimensions are A. So for a face-centered cubic structure, so there will be 8 items on the corner and 8 items on the 6 items on the faces. So these will be the 6 items on the faces. Anyway, so if I take this direction, so this side will be the length A, okay, and there will be 2 atoms over here at the corners. So for this dimension 100, this direction 100, one of this atom is the half atom, the other of this atom is also half atom. So there are 2 half atoms. So that means equal to 1. This is the number of atoms for this direction. And what will be the length? Length of is, as we know that it is A, but this length we need to find in terms of the radius. So this length can be found by considering the diagonal. Okay, as you can see in that, for the face-centered cubic structure, the face diagonal will be equal to this base length A and then the height also A. So that means we are talking about this A and this A, and then we are taking this face diagonal. Okay, so face diagonal is equal to 4r. Why? Because there is a atom here, there is an atom in the middle, okay, and there is an atom at the corner, so 4r, and then these are the lengths as base and height are A. So applying the Pythagorean theorem, it will be a square plus a square is equal to 4r square, and then if you simplify it, then A will be equal to 2 under root 2r. Okay, so since this length is equal to A, so the linear density for face-centered cubic 100 direction is equal to 1. Number of atoms are 1 divided by 2 into under root 2r. Okay, for the other direction, which is actually this direction. Okay, so if I quickly draw this direction like over here, so if this is the y-axis, this is the x-axis, and this is the z-axis, so this is 0, so 1 1 1 point will be here, 1, okay, 1 and 1, so this will be 1 1 1, so this will be the body diagonal. Okay, body diagonal, so 1 1 direction is the body diagonal, so this is the direction 1 1 1. The length will be equal to the body diagonal. Okay, and there will be how many atoms? So one atom will be at this corner, the other atom will be at this corner, and there will be no other atom because all the other atoms are the face atoms. So face atom will not be there in this body. Okay, so two atoms, so therefore number of two half atoms, so therefore number of atoms are also 1 in this case. 2 by 1 by 2 is equal to 1. So number of atoms, and the length is the body diagonal. So this body diagonal is equal to is equivalent to this face diagonal plus this height. Okay, so the face diagonal is here, okay, and then height is here, height is a, and then this is the body diagonal. So body diagonals, face diagonal we have already determined is 4r, and a we already know that it is 2 under root 2 r. So face diagonal square is 16r square plus a square is 8r, and body diagonal is equal to body diagonal square. So body diagonal square will be equal to 2 under root 6. 16 plus 4 is 24, so that makes this 2 under root 6r. And then in this case, the linear density for the face centered cubic in the direction of 1 1 1 will be equal to 1 divided by 2 under root 6 r. Okay, so these are the two expressions. So for part B, it is asked that silver. Okay, so linear density dimensions for these same two directions for silver. So for silver, the atomic radius is this can be found from the book, or one can search from Google. So atomic radius for silver is equal to 0.144 nanometer. So if I put for this 100 linear dimension for silver, okay, in the linear density for silver in the 100 direction, so it will be equal to 1 divided by 2 into under root 2 r 0.144 nanometer converted into meters, so it will be this. And then if you will calculate it, the answer will be equal to 2.46 into 10 to the power 9 per meter. Okay, so the dimension and the unit is per meter, or maybe it's more appropriate to say that 2.46 into 10 raised to the power 9 atoms per meter. Anyway, so per meter is the unit. And similarly, if we put find the linear dimension, linear density for 111 direction, so we can input the same values for 111, and then if you will calculate it using this formula, okay, not this formula, using this formula, it will be equal to 1.42 into 10 to the power 9 per meter. Okay, so this is the answer.